Hello everyone, I'm Zhiyi, a second-year student, a PhD student of Fudan University. Today I'm glad to share our work, Holmes, Localizing Irregularity in Large Language Model Training with Mega-Scale GPU Cluster. This is a joint work with Tencent and the University of Chicago. Today's large language model training often requires thousands of GPUs. To efficiently utilize this GPU resource and network infrastructure, current training systems often employ multiple parallel training strategies. Although these strategies improve the training efficiency, it also introduces massive cross-device communication and operational coupling between devices. So, a critical question is that how to ensure the reliability of large-scale training in mega-scale GPU cluster. Existing approach predominantly focused on addressing failures during training. When a device failure occurs, the training has to stop immediately. Engineers will replace the failed device and restart the training. To minimize such cost, current research devotes to design faster checkpointing mechanism and reliable training mechanism. While existing solution handling failures, a critical question remains: does eliminating failures ensure stable training? Ideally, each training iteration should be a duplication of previous one because we are repeating the same tensor computation and identical communication patterns. So as a result, the iteration time should be consistent during training. However, in the training with thousands of GPU, we observe something counterintuitive. Even in a cluster without any failures, the training iterations show unpredictable variation, which we termed irregularity. In this figure, we show an example of irregularity we call abnormal spikes. The iterations that we marked with the crosses have a much longer iteration times than the others. We also depict the primary causes of the abnormal spikes, including GPU execution, network issues, and others. Here we show another two examples of irregularities. In the left figure, we show the irregularity called fluctuation, which is often ignored due to their inconspicuous variation magnitude over individual iteration time. At the top of the figure, the iteration can reach 9.5 seconds, while the average iteration time is only 8.4 seconds. However, since the fluctuation is much more frequent during training, it can significantly increase the overall training time. In the right figure, we illustrate an irregularity we call persistent degradation. Here, we can find a training throughput decline from 150 samples per second to 125 samples per second. Although the decreasing process of throughput itself lasts for only 50 minutes, after that, the training will execute at a low throughput if the degradation is not addressed in time. Next, we will show how irregularity impacts the training process. In our experience, we define irregular iteration as those where iteration time exceeds the average duration by a fixed margin. So as shown in the left figure, irregularity has high frequency during training. Meanwhile, the frequency of irregularities increases as more GPU are used. The middle figure compares the time wastage between failures and the irregularity. The results show that irregularity-induced time wastage is tantamount to failure-related downtime. As shown in the right figure, over 80% of the irregularity localization attempts require more than 3 hours to complete, which is much more longer than typical failure diagnosis periods. This is because failure has been extensively studied, and now we have lots of tools to help us conduct failure diagnosis. However, for the irregularity, we do not have such mature method. So this also motivates us to design an automatic system to localizing the irregularity. However, designing such a system has 3 challenges. First, irregularity behavior can propagate, as shown in the figure. When one GPU slows down during computation, all the other GPU must wait and subsequent synchronization. So this creates misleading observations while the prolonged iteration time appears across all the GPUs, masking the root cause of the problem. Secondly, irregularity occurs silently with training process. Unlike failures that generate error logs, irregularities do not haunt the training process. This necessitates proactive monitoring mechanisms that can detect irregularity without interfering with the normal training. Thirdly, misidentifying the irregularity is costly because when the irregularity occurs frequently, misidentifying can lead to the waste of precious GPU resources and leave the irregularity unresolved. To address these challenges, we propose Holmes, a system that pinpoints irregularity through communication operator analysis. Holmes begins by monitoring the iteration time on a single GPU. When the iteration time in this GPU exists the average iteration time by delta times, Holmes sequentially examines each communication operator in this GPU to identify those results in the iteration delay. Once detecting an operator with prolonged execution, Holmes therefore cross-checks all the GPU executing the same operator. In this step, we model the relationship between operators and the GPUs and use a novel algorithm to localize the root cause recursively. By aggregating localization results across multiple iterations, Holmes statistically identifies the most probable anomalous devices. So Holmes monitors the training and localize irregularity by exploring abnormal communication operator. Our key insight emerged from operator dependencies in training iteration. Since communication and the computation operator are interdependent, we can detect both types of the issues through communication operator alone. For instance, communication issues directly manifest themselves in their operator's execution, while for the computation issues, we can infer them through the delayed initiation of its dependent communication operator. Then, by focusing on the sparser communication operators rather than dense computation operator, our monitoring imposes negligible overhead. Thus, we design and distribute a communication operator logger across all the GPUs, capturing the essential operator data including types and durations. To confirm the abnormal operators, we employ the random forest model for each operator and design domain-specific operator features as shown in the red diagram. Our random forest model can accurately predict abnormal operators. However, during our development, we found that the prediction performance is impacted by the distribution drift. As shown in this figure, the daily average iteration time of both the training varies over months. Instead of retraining the random forest model periodically, Holmes automatically adjusts the decision tree threshold. For example, when the iteration time shifts by 0.2 seconds, corresponding tree nodes will be updated. This approach maintains the accuracy with minimal human efforts. Having the identified abnormal operators, we need to localize the true source of irregularity while avoiding the misdiagnosis from remote GPU anomalies. Firstly, Holmes constructs a communication operator graph which models the relationship between communication operators and GPU devices. Our principle is to leverage the grouping nature of parallel training strategy. Each communication operator inherently belongs to a specific parallelism group like a tensor group or data parallel group. By modeling relationship between those through this established parallel group rather than individual GPUs, we dramatically reduce the graph complexity. We then move to the core localization algorithm of Holmes. Our algorithm leverages a key observation. Abnormal communication operators may actually be waiting for the slower GPUs. This example shows a TP-R-reduced communication. GPU 3 experiences prolonged computing, but its communication operator remains normal. And as this is a collective communication operator, so all the others wait for the GPU 3 to start. In this case, GPU 3 with normal communication operator is the root cause. Well, this pattern also holds in our PP communication case. So based on these critical insights, our localization algorithm follows these two principles. For prolonged communication operation, if any participating GPU shows normal operator status, while all the others exhibit abnormal, that specific GPU with normal communication operator is identified as the root cause. If all the GPUs involved in the communication show abnormal operator status, we conclude that the communication itself is the source of the problem. Then we use a case study to show how our localization algorithm works. The training in this case is executed on the typical 3D parallelism. In this case, the iteration time increased by 10 seconds. Starting from monitoring in the GPU 0, we observe an abnormal standard operator belonging to PP parallelism. Along the pipeline, we found that the corresponding receive operator of this send in GPU 384. However, the receive operator is normal. Instead, we detect another send operator preceding the receive operator, which is abnormal. We keep searching on this send. After repeating multiple rounds, we transition to this GPU, whose reduced operator of DP is found abnormal. The reduced belongs to DP group 24. We then detect all the GPUs in the DP group. Only one GPU's corresponding reduced is normal, while the other GPU have the same abnormal DP reduced operator. This indicates that this GPU is the straggler, and the rest of the GPU starts the reduce ahead of this GPU, and just wait until it's prepared. So in this GPU, the abnormal operator we can detect is an altogether belonging to TP group. Keep searching in this group, we found the same altogether is normal only in GPU 2574, whereas no other abnormal operator in this GPU. So we can infer that the irregularity is caused by the GPU 2574 computing slope. Finally, we conduct cross-iteration analysis to improve the localization accuracy. Holmes ultimately identified the top 2 anomalous device candidates. For evaluation, we collect our communication operator logs over 3 months from our production training cluster. Meanwhile, localization latency is evaluated in our production network environment testbed. The models we trained include Llama series and GPT series with hundreds of billions parameters. Our ground truth is obtained by manual diagnosis. Firstly, we rely on expert knowledge to enumerate all the possible anomalous devices. Subsequent manual inspection evaluates device resource metrics like GPU utilization. Suspected devices are isolated upon confirmation through stress testing. Since there are no existing systems for irregularity localization during training, we adapt the idea of 2 anomaly diagnosis methods of microservice as our baselines. The figure in the left shows the end-to-end localization accuracy when training models at various GPU scales. The result shows that Holmes can achieve the highest accuracy. As shown in the right, even with 6D parallelism, Holmes' media localization accuracy reached 86%, which shows that Holmes is adaptable to existing parallel training strategies. We then evaluate the overall localization latency of Holmes when training with different cluster scales. The result shows that Holmes significantly outperformed the traditional approach, which analyzes all the GPU logs centrally. Well, the cumulative distribution of the latency shows that near 90% of the overall latency value fall below 30 seconds. To show the performance of our system components, we conduct modular study. The result shows that our communication operator logger have trivial impact on training efficiency. Meanwhile, our abnormal operator detectors show better detection accuracy against distribution drift, and our localization algorithm can reduce 96% of the log data transmission. We conduct more comprehensive experiments to validate system effectiveness in our paper. To conclude in this work, we systematically measure and analyze the irregularity phenomena in large language model training. Considering the communication of the model training, we design a system for localizing irregularity from network perspective and experimentally demonstrate its effectiveness. And we hope our early steps can inspire more innovations. That's all, thank you. And I'm happy to take any questions.